Hello everyone, my name is Stefan, and in previous lecture you have already heard what the 500 Hz tone sounds like through this audio sync. But now we will take the next step, we will visualize its waveform. Seeing the waveform in action not only confirms the behavior of your flow graph, but also deepens your understanding of how signals behave in the time domain. The section introduces the Q2 GUI time sync block, a powerful tool for monitoring signals. Think of it as your signals diary, showing what signal is doing at any given moment. Let's dive into the process of visualizing the tone while exploring some foundational concepts. So you might ask, what does it mean to visualize a signal? When we talk about visualizing a signal, we are referring to graphically representing the amplitude of the signal over time. This allows us to confirm the signal's behavior matches our expectations, detect unexpected distortions, anomalies, or noise, and develop an intuitive sense of frequency, amplitude, and other properties. In the case of our 500 Hz tone, the visualization will help you confirm that this signal is pure signal frequency tone represented by a sinusoidal waveform. To bring this visualization to life in GNU Radio, we will insert the GUI time sync block into your flow graph. In the block properties here, set the type to float. This ensures it processes the floating point data stream generated by your signal source. And we will attach the output of the signal source to the input of the GUI time sync. Leave the signal source connected to the audio sync so you can still hear the tone while visualizing it. And now we will run the flow graph. Let's make it big here. And along with the hearing the tone, a graphical yeah, along with the hearing the tone, a graphical window will appear, displaying the signal as a function of a time. In the display window, you will observe a sinusoidal waveform oscillating smoothly between the maximum amplitude of 0.1 and minimum amplitude of minus 0.1. The repeating pattern represents a 500 Hz tone, where the frequency corresponds to how many cycles or peaks and troughs occur per second. To better understand the waveform, we have three options. The first is mouse screw zoom, the second is box selection zoom, and the third is nested zooming. So let's go with the first, mouse screw zoom. You can use your mouse wheel to zoom in or out vertically, adjusting how much of the amplitude you see. And you can also click and drag your mouse to drop a box around the specific section of the waveform. When you release the mouse button, the display zooms into that region. You can repeat the box selection to zoom further into specific details, such as a single oscillation, and you can use the right mouse button to undo zoom levels incrementally, like the first right hand click, second, and third. And when you zoom in far enough to focus on a single up and down segment of the waveform, you will see the classic sine wave shape. So you might ask, why does the 500 Hz tone look like a sine wave? This ties into fundamental properties of pure tones. A pure tone consists of single frequency, which mathematically corresponds to a sine wave. Here's why. The sine waves are the simplest periodic signals. In audio terms, they represent the cleanest sounds possible to devoid any harmonics or noise. Any real-world sound can be broken down into a combination of sine waves. thank to, thanks to Fourier's theory. But a single sine wave is as pure as it gets. By visualizing this tone, you are witnessing the building block of more complex signals. In real-world signal processing tasks, visualizing signals is essential for debugging, quickly spotting if something in your flow graph isn't working as expected, understanding signal behavior, developing an intuition for concepts like frequency, amplitude, and phase, and for optimizing designs, ensuring your flow graph produces the desired outputs efficiently. The combination of audio and visual feedback enriches your understanding of signal, while your ears confirm the tone's presence and time sync confirms its purity and periodic nature. Now that we have visualized a 500 Hz tone, let's push the boundaries to explore the audible frequency spectrum. This is where things get interactive. No more stopping or restarting the flow graph every time you want to try a new frequency. Instead, we will integrate a real-time control mechanism to adjust the tone dynamically and make the experiment more intuitive. Manually editing the frequency in the signal source block, stopping the flow graph, and restarting it for every new frequency can quickly become tedious. What if you could slide between the frequencies while the flow graph is running? We will enter the GUI range block. This is a versatile tool that provides a graphical slider for real-time adjustments. And we will add this to our flow graph. And here's how you can set up your flow graph to adjust frequency dynamically. And we will put it here. This is not a variable, to be honest, but let's put here. And we will open its properties. We will set the ID to frag. So you will use this ID later in the signal source. Default value to 500. Start we will set to 100 Hertz. This is the lowest frequency you can select. The stop to 32,000, so 32 kilohertz. This is the highest frequency you can select. And the step, let's set to 100 Hertz. This is the increment value for each slider tick. And we will click on apply. Okay. In the signal source block, we will replace the static frequency value to frag. This one. This is the matching the ID with this GUI range. Click on apply. Okay. And keep the signal source connected to time sync for visualization and audio sync for playback, for hearing sounds. Once you execute the flow graph, a graphical user interface window will appear with two main elements: a sinusoidal waveform display in the time sync block and a slider from the range that lets you adjust the frequency in real time. As you move the slider, let's actually, yeah. As you move the slider, hmm, so as you move the slider, the tone's pitch will change dynamically. The waveform in the time sync will adjust, oscillating faster or slower depending on the frequency. And let's analyze what happens as you interact with the slider. You will notice let's actually close it and change the value a little bit. So we will start widget. Let's actually start to 10 hertz and step to, let's say, 10. Let's start it. And here we are. Now we will go below the 20 hertz here. You will notice this slow moving sinusoid in the time sync block. However, you won't hear much because these frequencies are below the human auditory range you learned in previous lectures. And let's go, as you know, human hearing range is from 20 hertz to 20,000 hertz. As you increase the slider value, the tone pitch rises and the waveform oscillates faster. Most humans can hear the tones up to 16 hertz. To be honest, I'm not hearing this, depending on and that also it depends on age and hearing ability. And beyond the 20,000, let's say 25,000, right? Ooh. While this time sync will still display its waveform, your sound card or speakers may struggle or even like uh, to produce these tones accurately. So what we are hearing is not 25 hertz, 25,000 hertz sound. It's what our speakers are struggling to. And if it will be 25,000 hertz sound, we won't hear it. So while this time sync will still display this waveform like this, it's here. And you might also observe the aliasing effects where the tone's pitch unexpectedly drops instead of rising here. So this occurs because of aliasing, a fundamental concept in signal processing. Here's a simplified explanation. The sample rate of your flow graph is, let's say, 32 kilohertz, like this, meaning the system captures 32,000 samples per second. According to Nyquist theorem, the maximum frequency you can accurately represent is half the sample rate. In this case, it is about 16 kilohertz. And frequencies above this threshold appear as lower. Let's see, like this. Oops. Here. And also it appears lower and aliased frequencies due to undersampling. And aliasing is a key reason why high fidelity audio and precise signal processing require adequate sampling rates. It underscores the importance of choosing a sample rate that's at least the twice the highest frequency of interest. And at this point, you might be wondering, what's the big deal about frequency? Here's why it's critical. Signal identification. Frequencies are unique identifiers for signals. For example, radio stations are assigned to specific frequencies. It also matters for filtering. By isolating certain frequencies, you can remove noise or extract desired signals. And also communication. Frequency manipulation is the basis of technologies like AM, FM radio, Wi-Fi, and cellular networks. Whether you are working with audio, radio, or even medical signals, understanding and controlling frequency is fundamental. Before diving deeper into frequency manipulation, it is worth mentioning that all these concepts tie into a larger framework called frequency domain, While we've been visualizing signals in the time domain, amplitude versus time, many real-world applications analyze signals in the frequency domain, which is amplitude versus frequency. This standardization will unlock powerful tools for signal processing, but for now, keep experimenting with your frequency slider to build a strong intuition about how signals behave. This range block doesn't just make frequencies adjustment easier, it also bridges the gap between theory and hands-on experimentation. By dynamically controlling the frequency, you have experienced the interplay between pitch, waveform, and aliasing. Keep these principles in mind as you move forward. Frequency is one of the most powerful tools in your signal processing toolbox. I'm Typhoon, and I'm meeting you in next lecture.